Hi dear friends, myself Bhausab Sonone, Assistant Professor, Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College Jawar, District Palghar. Dear friends, in the previous lecture, we discussed about the radioactivity disintegration, and in that lecture, we came to know that according to Soddy and Rutherford, the rate of disintegration of any radio element is always directly proportional to the total number of atoms present at that instant, just like the rate law. Based upon the same statement, we had derived an expression for the decay constant of disintegration of any radioactive element, and we got the equation for a decay constant. Based upon the same, today in this lecture, we are going to discuss the characteristic of decay constant of radioactive disintegration of radio element. But before going to discuss the characteristic, I would like to revise the expression for the radioactive decay constant that we had derived last time. Dear friends, suppose in this lecture we will revise this. Suppose we will consider this NT. N suffix T is the number of atoms of radio element at any given time. Hence, the rate of disintegration, which is also called as the rate of decay of radio element, is indicated by minus dNt by dt. This minus dNt by dt is the equation for rate of disintegration of radioactive element. This dNt, this is the change in number of atoms of radio element, and dt is the small change in time. So change in number of atoms to the change in time means change in concentration to the change in times is called as the rate of disintegration. Negative sign indicates the number of atoms of radio element decreases. So this rate of disintegration of radio element is directly proportional to number of atoms present at that instant, and that number of atoms indicated by means NT. So in order to remove the proportionality sign, we had taken the constant, and that constant is called as the decay constant. This is very simple. So that's why we got the equation minus dNt by dt is equal to lambda into t. Then we had written the equation for lambda, which is decay constant, and if this dt is unity, change in time is unity, then we got the equation minus dNt by dt minus dNt upon Nt is equal to lambda. Hence, this decay constant from this equation can be defined as this dNt, change in number of radio element atom. So this is change in number of atoms, or this is the number of atoms which undergoes disintegration, and Nt is the total number of atoms present. So this is change in atom to the total number of atoms. So this is called as fraction. That's why radioactive decay constant is the fraction of total number of atoms which disintegrate in unit time. In unit time in the sense dt. So this fraction of total number of atoms which disintegrate in unit time is called as decay constant, indicated by lambda. So from this equation, we are going to derive the equation for decay constant lambda as integrating this equation between the limits of n0 and nt. So limit of n0 will be n0 at time t is equal to 0, and nt will be at time t is equal to t. So after simplification of this, after taking the integration between these two limits, we got the equation ln of nt upon n0 is equal to minus lambda t. Later on, we are able to convert this equation into exponential form, and that is given by the equation nt is equal to n0 into e raised to minus lambda into t. Here, if this natural log is converted into log to the base 10 by multiplying 2.303, then definitely we are getting this equation, and it was our last equation a final equation that we had derived in the previous lecture. Lambda is equal to 2.303 upon t log to the base 10 of n0 upon nt. So this is very simple, that in this equation, from this equation we are able to derive, we are able to calculate the decay constant of any radioactive disintegration of any radio element. In this equation, I hope you are able to define the meaning of all terms. Lambda is already, I told you, decay constant. T is the time, either in second, minute, hours, whatever. N0 is the initial number of initial number of atoms of radio element. Nt is the number of atoms of radio element at any given time. So this is nothing but simple, and from this equation we are going to derive the different characteristic of radio element. So it was just a revision of the previous lecture that we discussed. So now next we are going to discuss about the characteristic. Here from this equation, the first is the unit of decay constant. In order to derive the unit of decay constant, if you see this, then we got the equation for decay constant as lambda is equal to 2.303 upon t log to the base 10 of n0 upon nt. Here in this n0, it is the number of atoms of radio element, and nt, it is also number of atoms of radio elements. So both are the similar quantity, both are the identical quantity, so that will get cancelled. And in this equation only one term will remain, and that is time. That's why if we'll discuss about the unit of decay constant lambda, then we are just getting the reciprocal of time. So reciprocal of time is the unit of radioactive decay constant of any radio element. That's why the actual unit will be either per second, per minute, per hour, per day, etc. So this is reciprocal of the time. So given time will be converted into reciprocal, and that will be the unit of decay constant. It's very simple to discuss the characteristic. That is, first unit of decay constant, that will be always per time, and it is just like the first order reaction. Next characteristic is the half-life of radio element. But before discussing the half-life of any radio element, you should know what is half-life. Half-life of any radio element, it is the time required for the number of radioactive element or the radioactive atoms to be reduced to half of its initial value. So it's very simple. It is the time required to decrease the number of atoms of radio element to half of its original or the initial number of atoms. Suppose it means that, suppose initial number of atoms are for example 100, then how much time is required to reduce this number of atoms to the value which is initial, that is half of the initial, means 50. Then so as the initial value is the 100, and the time required to reduce this number of radioactive element to 50, which is the half of the initial. Suppose for this change we are requiring, that is 1 hour, then this 1 hour will be the half-life period of this radio element. I hope you got the idea about the half-life period. Half-life period is the time required for the number of radioactive atoms to be reduced to half of its initial value. Because as the disintegration process, as the time process, disintegration will proceed, and definitely the number of atoms will decrease. But how much time is required to reduce this number of atoms to half of its initial value? That much time, that much period will be called as the half-life period or the half-life time of radioactive elements. So this is very simple to discuss the half-life period. So here we are going to derive the general equation for the half-life period of any radio element, and how we can calculate the half-life period of any radio element from the decay constant. That is the purpose of our study. So here, as we told, that half-life period is the time required for the number of radioactive element to be reduced to half of its initial value. Already I have given one example. So initial number of atoms, suppose 100, then how much time is required to reduce this number of atoms to 50? So that much time will be called as the half-life period. So here, that's why the condition, for the half-life period will be number of atoms will be half of the initial. Here, initial number of atoms will be n0, that will reduce to, so that is divided by 2, so that will give you the value of nt. So nt is the number of atoms at any time, or number of atoms at the half-life period, and that number of atoms becomes half of the initial, means half of the n0. That's why the value of ent will be n0 by 2, and the period at the half-life of any radio element is always indicated by t suffix 1 by 2. So if we will put these values in the equation of decay constant lambda, then after simplification we will get the equation for half-life period. So this is very simple again. Lambda, which is decay constant 2.303 upon t, but t should be replaced by t 1 by 2 log to the base 10 of n0 upon nt, n0 divided by nt. Again this nt is replaced by n0 by 2, which is the condition at the half-life period of radio element. So n0 will get cancelled. Simply we are getting this equation that lambda will be equal to 2.303 upon t 1 by 2 log of 2, and you know very well this log of 2 will be 0.3010 into 2.303. After this we will get this equation that lambda will be equal to 0.693 upon t 1 by 2. Therefore we are interested to write the equation to get the equation for the half-life period of radio element, and that's why final equation for the half-life period will be t 1 by 2 is equal to 0.693 upon lambda. This lambda is the decay constant. So this is the equation. This is simple equation for half-life period of any radio element, and that is simple. Based upon the same, we will have some numericals, so that at that time we will see this. So this is the equation for half-life period of radio element. After discussing this, so here I want to point out one thing, that here in this equation which terms are included? Only t1 by 2 half-life period is depends upon what? Decay constant. It is not including any number of atoms of radio element either initial or at any given time. Hence we can say that half-life period of any radio element is always independent of number of atoms of radio element. This is very simple. Many times, or it can be asked to you in the true or false. So always remember that the half-life period of radio element is always independent of number of atoms of radio element, any number of either initial or at a given time. But this equation indicates that the half-life period of radio element does not depends upon the number of atoms of radio element. So this is another one. Next characteristic is the half-life, mean life, or which is also called as the average life. But before this, what is the life? Life of radio element or the atom of radio element, it is the time till which an atom of radio element exists without disintegration. You know very well, whenever we are saying the radio element, it has tendency to undergo disintegration, but still it has some time till which an atom of radio element exists without disintegration, and that much time will be called as the life of atom of radio element. And if you will take the average of such large number of life of various elements of the radio element, that will be called as the mean life or the average life. So here mean life or the average life of radio element is indicated by tau. It is indicated by tau. So it is indicated by tau. So this average life or the mean life of radio element is simply obtained by taking the reciprocal of decay constant lambda. Already we had equation for what? Already we had equation for the decay constant, and that the equation is nothing but simply decay constant will be lambda is equal to 0.693 upon t1 by 2. Here if we will try to derive the equation for the mean life or the average life based upon the same, definitely we will get the equation that this tau will be equal to 1 upon lambda, and if we put this value of lambda in this equation, simply we are getting tau will be equal to t1 by 2 divided by 0.693, and the reciprocal of this 0.693 will be equal to 1.44, and that's why this average time or the mean time will be always equal to 1.44 times of half-life period. Sometimes this can be asked to you, what is the relation between mean life or the average life and the half-life period? So always remember that the average life or the mean life of any radio element is always 1.44 times of half-life period. So this is very simple. Average life or the radio element is 1.44 times of the half-life period. So this how, based upon this mean life or the half-life period, if we will discuss some numerical, again you will come to know that how the numericals can be asked. Suppose here one numerical is given to you, that the activity of radioactive element falls to half of its original value in 5 hours. Calculate first decay constant, then average life, which is also called as the mean life, and the third one is the time required for the activity to reduce to 1/10 of its initial or the original value. So what things are given and what things to be calculated, this is very important to understand here. First of all, if you read the numerical very carefully, then you will come to that the activity of radioactive element falls to half. It means that the whatever initial number of elements are there, that number decreases to half of its initial value. So this is the time required for to reduce the number of atoms to half of its initial value, and that time is given here. How much time? This is the 5 hours. So this is the 5 hour. It means that it is the half-life period, because in 5 hours the initial number of atoms becomes half in 5 hours. Suppose this is very important to understand here. So this is the first quantity given. So you have given the half-life period, and this half-life period is equal to 5 hours. Based upon the same, he has to calculate the value of decay constant, means he has to calculate the value of lambda, and after calculating the value of lambda decay constant, we has to calculate the second mean life or the average life, means the tau, and last one is the time required for the activity to reduce to to 1/10 of its initial value or the original value. So this is the important, that what things are to be calculated. Suppose first of all, in the first part we will discuss about the calculation of decay constant. Then this decay constant is to be calculated, but for which only the value of half-life period is provided, because we have the equation for the decay constant lambda is equal to 2.303 upon t log to the base 10 of n0 upon nt. But here definitely the n0 and nt are not given, only their relations are given, that is half-life period, and time is also not given here. Instead of time, t1 by 2 half-life period. So that's why we are going to use the equation. That equation is simply lambda is equal to 0.693. Lambda is equal to 0.693 divided by half-life period t1 by 2, and that is equal to 5 hours. And by making the calculation, definitely you will get the 0.1386 per hour. So this is the value of what? Decay constant, which is having the unit of reciprocal of time, and the time is given here hours. That's why the reciprocal of time will be per hour. After calculating the value of decay constant, definitely it is very simple. It is very easy to calculate the mean life or the average life, because we know the relationship between mean life and the half-life period. So this mean life is the reciprocal of half-life, it is reciprocal of decay constant. That's why we have the equation tau will be equal to t1 by 2 upon 0.693. So here directly you can put the value of half-life period in this equation, or this 1 upon 0.693 will be always equal to 1.44. So here in this also you can put the value of half-life period. So 1.44 into half-life period 5. By multiplying this, we will get the mean life will be equal to 7.2 hours. So this is the second quantity that is to be calculated here. with the help of decay constant called as tau, means the mean life. After calculating the value of decay constant and the mean life, here we have asked here the time, we have asked here time required to reduce the activity to 1/10 of its initial value, because in this numerical it is given the activity becomes 1/2 in 5 hours, because as the time process disintegration is going on, disintegration also process, so definitely the activity of radio element also decreases. But in 5 hours, which is given here 5 hours as a half life period, it means that in 5 hours the activity reduces to half, so it becomes 1/2. So based upon the same, once the disintegration gets started, how much time is required to reduce the activity to 1/10 of its initial value, that time is to be calculated here, and that's why we are going to proceed for the same, that time, to calculate the time required to reduce the activity to 1/10 of its initial value. For that purpose, definitely we are going to use, as we are interested to calculate the t, so definitely we are going to use the equation for decay constant lambda is equal to 2.303 upon t log to the base 10 of n0 upon nt. Then what values are known and what values to be calculated? Definitely time is to be calculated. Lambda is also calculated by us in the first part of this numerical. n0 and nt, these are the unknown values, but we know and we don't know the exact value, but we know the relation, that is here we are going to calculate the time for which number of atoms at a given time becomes 1/10 of initial value. So we can derive, we can get the relationship between n0 and nt, and definitely here, as just like the half life period, nt becomes half of the n0, and here the difference is that nt will become 1/10 of n0. So here definitely it's very simple, that so means if suppose the n0 is equal to 1, the nt becomes 1/10. So here it's very simple, that is n0 and nt, it means that n0 is 1, then time is required to be calculated, time is to be calculated for the 1/10 of 1 n0, means nt becomes 1/10. So if you put the value of n0 and nt in this numerical, and by making the calculation, definitely you will get the 2.303 upon 0.1386, which is the value of decay constant. Log 10, log 10 is 1, and by making or by simplification this term, simply we are getting time required to reduce the activity to 1/10 of its original value, initial value is 16.61 hours. This is very simple numerical, and based upon the same numerical you can solve the other numerical also, but this is one of the example for which we can go for the we can try to solve another numerical also, but this is numerical based upon the half life period and the mean life, as well as the decay constant that we had derived last time. So this is very simple to discuss here. This, I hope you will get the idea about the numerical also. Actually friends, after discussing this numerical, we are interested to discuss some phenomenon regarding with the radioactivity, because till this we was discussing about the disintegration of radioactive element, and this disintegration of radioactive element is discussed with the help of decay constant lambda. But at the same time, it is also important to know the type of radioactive disintegration and how we can measure this radioactive disintegration, means radioactivity. Then in the earlier lecture we discussed that the various types of radiations are emitted by a different radioactive element based upon their mass number and the atomic number. That radiations may be alpha radiations, it may be beta radiations, or it may be the gamma radiation, and based upon the type of radiations emitted by the radio element, these type of radio activity are, or the radioactive radiations are alpha, beta and the gamma. So based upon this type, again there are different decay, there are different types of decay, either alpha decay, beta decay, or the gamma decay. That types based upon the type of radiation emitted by the radio element. But here in this, we are interested how we can identify, how we can detect which type of the radiations are emitted by radioactive element. This is very important, that here we are not going to identify only, but we are going to identify the type of radiations emitted by the radioactive element, because once the type of radiations emitted by the any radio element is identified, definitely we will be able to find out the type of decay of radio element, because this type of decay is very important to know the relationship between mass number and the atomic number of daughter element as well as parent element. So that's why the detection and the measurement of radioactivity or the radioactive decay is very important, and there are three types. But how we can identify whether the alpha radiations or the beta radiations or the gamma radiations are emitted by this radioactive element? Then it is possible to detect and identify these radiations emitted by radioactive element with the help of this radiation, because these radiations are able to produce the ion pairs. How these are able to produce the ion pairs, and how these ion pairs are helpful to find out the type of radiation, that we will discuss later on. But the whatever radiations emitted by the radio element, these radiations are able to produce the ion pairs whenever these are passed through some inert gases. So this is the important. So whenever this alpha, beta, or the gamma radiations are passed through inert gases, then these are responsible to produce the ion pairs, and these ion pairs will be helpful to identify the type of radiations emitted by the any radio element. So what happens actually, these ion pairs migrate towards the electrodes of opposite charge. Whenever we are seeing the oppositely charge, it means that one electrode will carry positive charge, another electrode will carry negative charge. So one will be anode, another one will be cathode, and out of this ion pairs, one will be electron deficient, means the positively charged species, another one will be electron rich species, means negatively charged species. So they will migrate towards the oppositely charged electrodes, and where they will get discharged to produce the current, and the magnitude of this current will give a type of ionization, and this type of ionization will be helpful to identify the type of radiations emitted by any radio element, because the type of radiation which depends upon which type of radiation is responsible to produce the current, and this type of radiation is more, or sorry, number of radiations are more, ionization will be more, there will be more current in terms of magnitude. And it was observed that a particular alpha particle is able to produce around 10 raised to 5 number of ion pairs per centimeter, while beta radiations is able to produce only around 10 raised to 2 number of ion pairs per centimeter. So that's why this number will helpful to distinguish the magnitude of the current, and that definitely from this value we will be able to distinguish between the type of radiations emitted by the radio element, because for the alpha radiation it will be more, and for the beta it will be smaller. And the number of particles emitted by any radio element, so whenever you want to detect, whenever you want to measure the particles or the radiations emitted by any radio element, then that particles emitted by any radio element can be measured with the help of two counters, two devices. One is called as the Geiger-Müller counter. In short, it is called as GM counter. And the second one is called as the scintillation counter. Scintillation is the terms that is regarding with, or that is, it indicates the flashes of light, and that's why it's scintillation, that's why it is called a scintillation counter. So these two are the counter which are used to identify and to detect and to identify, to measure the type of particles emitted by any radioactive element that we will discuss in the next part of the lecture, or in the next part of the video of the lecture. Okay, so we will resume again in the next video to discuss about the GM counter and the scintillation counter. Thank you very much.